Hello everyone, and welcome back to the Automobile Seminar. So today we have a very special guest who I guess doesn't really need any introduction in this community here. We have Frank Carter with us here today, the godfather of Automobile. Frank is a professor at the University of Freiburg, PI at the Alice Institute, and the CEO of Prior Labs. He holds two ASC grants, an Eminenta grant, has organized countless workshops on Automobile, meta learning, Bayesian optimization, and set up the Automobile conference. And yeah, he even somehow managed to get me through my PhD. And today he will be talking about their new TabPFN model, which already made quite a big splash in the world of tabular data and time series prediction. And yeah, with that, thanks, Frank, for joining us today, and floor is yours.
Yeah, thank you so much for the intro, Aaron. It's great to be here, and yeah, great to see so many of you here. Yeah, today I want to talk about, of course, TabPFN, but also in general more like tabular foundation models. That the fact that I do think that they will usher in a new era of data science. With the example of TabPFN, I also want to give a bit of an intro to PFNs, Prior-data networks. They do actually interact a lot with the AutoML community other than just for tabular data. So I also want to mention a bit on that. But yeah, setting the scene for tabular data. So foundation models, of course, have revolutionized reasoning on text and on images. But on tabular data, which is sort of a poster child of AutoML, the deep learning revolution hasn't actually arrived. Yet, actually, in the enterprise, our most valuable data is actually organized in tables. Think spreadsheets and relational databases. And our vision is that, well, what if we could actually understand tables as intuitively as we understand images? Again, at the end of the day, I think an image is 1,000 pixels times 1,000 pixels. A table is 1,000 rows times 1,000 columns, maybe. But we as humans, we have not evolved to understand tables as easily as images. And well, neural networks, actually, the community has built them to resemble some parts of the human brain to actually work well on images, but the same mechanisms have not applied well on tabular data. Yet in the future, we hope to unlock this value to also get deep learning really effective on tabular data and get to the same types of breakthroughs as we have seen for text and images. And I think we as a community are on our way to revolutionize tabular data. We have been lucky to have this milestone in TabPFN v2 published in Nature that is actually more accurate than traditional machine learning methods such as XGBoost and CatBoost in 96% of the use cases we tried. And at the same time, actually also much more data efficient. So it was in particular the 50% of the data sufficed in order to get the same performance as the second best method on 100% of the data. And that is, of course, super useful in cases where there's just a sparsity of data, where we have rare diseases, for example, or acquiring new data is just really costly in terms of money or in terms of human suffering when you actually want to develop a new medication or whatnot. So it really unlocks some new possibilities for applying machine learning. All right. Talking about foundation models are particularly known in language models these days. And you can think of tables as the language of science, business, and the enterprise. So thinking again, Excel spreadsheets and databases. So for example, here's these four different areas: healthcare, finance, business analytics, insurance. In each of these, there's lots of tabular data. There's even more tabular data in many other fields. Like in particular, actually, since we launched the Nature paper, we're getting a lot of requests from retail kind of communications, also energy, regional energy suppliers, manufacturing. The manufacturing industry has lots of predictive maintenance tasks and so on that are tabular. So there's really thousands of possible applications of tabular data. But actually, just sticking with these four verticals for now. For each of these, I have a couple of examples here. For example, personalized risk prediction, or in finance, there's loan default prediction, or there's all kinds of customer lifetime value prediction in business analytics, or fraud detection in insurance, etc., etc. And these are clustered in tabular classification and regression problems, and also in time series and recommender systems. So there's lots and lots of possible cases, and let me drill down into one of them in order to make this really clear. What is tabular data? Not everybody works on tabular data. So here's an example from healthcare, one example among thousands again, where we have 5,000 patients for which we have measured some blood values, like omics values and blood markers, and we know whether they had early stage Alzheimer's or not. And then we have a new patient here, 5001, where we have the omics blood work, but we don't know whether they have Alzheimer's or not, early stage. And yes, we can wait like 5 years and then we know whether they had early stage Alzheimer's or not, but then it's too late to treat them. We want to predict this right now, whether they have it in order to treat it properly. And there's lots and lots of startups that are actually gathering this type of data. There's the billions of dollars worth in terms of data gathering. And in the end, this all actually comes down to tabular prediction tasks. So if we can actually come up with a better tabular machine learning method, it can really boost all these great work for humanity. This example also is useful for showing that existing solutions are not good enough. So for example, XGBoost or scikit-learn or whatnot, it just can't deal with something like diabetes. What is this? No, I need an embedding. I need to have numbers in there or categories. Missing values, what are we going to do with that? We need to have some missing value imputation method for most methods. What is early stage Alzheimer's? So the semantic information is just not there in the traditional machine learning methods for tabular data. And likewise, there's all kinds of other issues, in particular transfer of knowledge across data sets. So if you have hundreds of data sets from the same domain, you run XGBoost on each of them, it's going to start from scratch, and it doesn't actually learn across data sets. And that has been the big driver behind foundation models. So foundation models actually then also unlock this entire AI stack for tabular data. So we have open source software. We also have an API server that can be integrated in Python, Excel, language models, through a UI as a tool, for example. And then you can have all these use cases on top, and then application areas and all these different verticals on top. And the point of this slide here is that a tabular foundation model really underlies all of this. If we come up with a better tabular foundation model, then it has direct impact on all of these different types of use cases. Just like when OpenAI comes up with a new GPT right now, then there is thousands, maybe probably millions of different applications that could just directly use this and get better. And I do think that the future of data science is going that way. All right. Having this motivation, having given this motivation, now let's get a little bit more technical. So I do want to talk about TabPFN, but first I will talk about PFNs a little bit, Prior-data Fitted Networks. And this is a paper from 2022 already. It's called Transformers Can Approximate Bayesian Inference. And then TabPFN will just be a particular type of PFN with a prior over tables. And TabPFN 2 is basically the evolution of TabPFN 1. All right, let's get into PFNs. So PFNs approximate Bayesian predictions. This crowd here knows Gaussian processes well. And well, in Gaussian processes, you have a prior over functions. We just know a certain types of characteristics of these functions, such as their smoothness, etc. And let's say we have these priors over functions, and then we have some data points like these black ones here, and then the posterior over these functions is actually characterized by this prior here times the likelihood of the data under these priors and then a normalizing constant. computing this posterior over the latents that specify the functions, that is actually a intractable task. So what's typically used for that is Markov chain Monte Carlo or variational inference, but MCMC is quite slow, and variational inference is, well, the math is really hairy, and actually there is often approximation errors. And what we do actually with PFNs is to basically provide a third pillar next to MCMC and variational inference now in order to do Bayesian predictions. And we actually don't get a posterior over the latents, but we completely bypass the step and only get a probability distribution for the outcomes at a new variable. So we don't get like a posterior over all these functions, but we actually input the x, and then we just get a probability distribution over this slice here. And so with MCMC, you would actually have samples of your latents, and so this integral here would actually be a sum over your samples. And for variational inference, you would have some sort of a closed form formulation of this here, like a Gaussian, and then you have a Gaussian observation noise here, and then a Gaussian times a Gaussian, you integrate out is a Gaussian. That's how variational inference does it. We instead actually just tackle this here directly in a single forward pass and just bypass all the complexity of having to reason about the posterior of the latents. All right, that seemed mathy and abstract. Let's look at pictures for this. So all we need to do for PFNs is to actually sample functions from the prior. So that's one sample here from the prior. That's another sample. That's another sample. So these are samples of functions. And so we sample the latents from a prior. And we do that often. And then for each of these functions, we actually sample training data points and test data points. And we do that again for each of the functions. We don't need to have the same number of data points from each of these functions and not space the same, etc. And then, yeah, we do this millions of times because we can. This is a synthetic data generating process. And then we learn a PFN that gets the blue points as input and the X value for the orange point, and is tasked to predict the Y value for the orange point. And it's tasked to be able to do this for these millions of different cases. And when it has learned that, then it has learned for a new data set like this to get the blue points, get the orange X value, and then predict actually what is going to be the output here. And it can do that in a forward pass. It has been trained to do that. All right, so basically now we have meta-learned to approximate Bayesian inference purely by two ingredients. One is supervised learning, and we're just really good in this right now. Transformers work, SGD works, scaling laws work. This is sort of really being figured out by the community. And the other one is we need to be able to sample from our priors. And sampling from the priors is typically actually just very easy. It's very hard to quantify, what's the likelihood of this particular prior sample, whatnot. But we don't need to do that. We just need to be able to sample from the prior and then use supervised learning on that prior in order to basically capture the prior in the PFN and capture in the PFN the capability to actually do predictions with this prior. All right. So this doesn't only work in theory, it also works in practice. So here we use this in order to predict the posterior for a Gaussian process. And a Gaussian process is really nice because we can actually compute the true posterior Gaussian process in closed form. That is here in green. And in blue, there's slight differences to the green one. The blue one here is a PFN, and the green one is a true posterior GP. And if you train for longer, then even these differences fade away. And we have a theorem that actually, in the limit of infinite compute, we actually have the exact approximation of the true posterior. All right, for those of you who are more mathy, here's the same in formula. So we sample prior data sets and we train the PFN by minimizing the negative log likelihood of the data under this function. Then we have these fit parameters, theta star. So the PFN has these parameters. And then this Q function, that's a PFN with these parameters, that actually approximates the true Bayesian predictive distribution for new data sets. All right, the model we use for these PFNs, it's a permutation invariant transformer. So it's like a transformer, but actually we don't care about the order of the data points. We don't have a sequence, we have a set of data points. And so we treat it like this by just dropping the position and encoding. And then the test data points attend to the training data points. The test data points do not attend to each other. So that's why we cannot actually predict a full covariance matrix, for example, but we just predict the probability distribution for one given point at a time, given the training data points. And if we do want to draw joint samples, then we would have to first draw here this x4 and put it into the context, feed x1 to x4 into the transformer, and then sample x5 given x1 through x4. All right, the model head is actually regression as classification in order to be able to output multimodal probability distributions. So it's really, we have somewhere between 500 and 5,000 different bins, and then basically just predict a histogram over these bins. And we also have a version where the leftmost and the rightmost bin are half Gaussians in order to avoid a case where, for example, this data point here has zero probability. Zero is always bad as a probability because then you could get divisions by zero pretty quickly. Let's rather give it a very small probability. All right, yeah, the results, it's also good at approximating more complex Gaussian processes in contrast to previous methods such as attentive neural processes. It's also, when you look at Gaussian processes with unknown hyperparameters, then you can't do this computation in closed form anymore. Then you do need MCMC or variational inference. And there, yeah, the PFNs are actually just much better in terms of the approximations, and they're also much faster. So they get the same results in terms of negative log likelihood here as stochastic variation inference and the no U-turn sampler, that's an MCMC method, in like 10 to the 2, 10 to the minus 2. So that's sort of like 10 to the 4, like 10,000 times faster for getting the same negative log likelihood just by doing a forward pass. And these are tiny Bayesian neural networks here with like 3 features and 8 features so that we can actually do these computations for MCMC and variational inference. We don't care for our methods how big these BNNs are. They could have millions of parameters because we don't actually give a posterior over the parameters. We just give the posterior over the probability distribution, over the integral over all the possible weights of the network rather than a posterior over the weights and then multiply by the observations given the weights. So we're independent of the number of parameters in the network here. Our PFNs also enable like basically Bayesian deep learning in a forward pass. So there the prior would be the weights of a given neural networks, and the posterior predictive would be the Bayesian neural network. And so that's visualized here. So we have the inputs, and then we have a single neural network where we have an uncertainty over the weights. And there was a previous slides where you're like 10,000 times faster than MCMC. But we can also do things where we actually don't know what is the right architecture. So being Bayesian typically means we want to actually admit our uncertainty about the parts of the model that we're uncertain about. and typical Bayesian deep learning, just as well we're uncertain about the weights, but really we're also uncertain about what is the right architecture for the data at hand. And we would like to be honest about that, and then integrate over the probability distributions of all of the different architectures with all of the different weights and how likely they are given the data. And so you can actually do this really trivially with PFNs by not just having a probability distribution over the weights, but also probability distribution over the architectures. So you first sample an architecture like this or this or this, then you sample weights in there. You sample your X variables and your Y's, and then you do this millions of times, and then you have a data set that you fit your algorithm to, and that algorithm actually then learns to integrate over all these possibilities of all the different architectures and the weights. And so you could see this as sort of Bayesian neural architecture search, except that it doesn't actually tell you which architectures it uses. It just tells you the integral over all the possible architectures. And this would be extremely hard with MCMC. You would have to do some crazy reversible jump MCMC over different types of architectures and so on. So it really opens new doors for this by this flexibility of only having to sample the prior. There's various follow-ups of PFNs. Actually, this slide is not quite complete. I think there's tabular data such as TabPFN. There's also time series forecast PFN. There is Bayesian optimization. I do have some slides on that. There's also medical images. There's some genetics. There's some EEG work by now. There's really quite a lot of PFN follow-ups now. And I do encourage you to look at PFNs. They're really a cute tool. I mentioned I'll talk about BO. So Sam has actually looked at replacing the Gaussian process in Bayesian optimization with in-context learning. And this can be done. And in particular, this is just really nice and easy to work with. So if you want to have a prior or if you want to have a GP that can deal with non-stationarities in your data, or with heterogeneous noise, or with change points, or with any of these annoyances, it's very hard to do in GPs. And all that it changes for PFN is just a change in the prior. And other than that, you just turn the crank and train a new neural network when the prior changes. Likewise, we have used this actually for learning curve prediction. Here, there's a nice anecdote. Learning curve prediction can be done with MCMC, where we have priors over different learning curves, like different parametric learning curves that are growing and at some point stagnating. And actually, the first ever master thesis that I supervised at Freiburg was by Tobias Domhahn, and it was precisely this, MCMC for learning curve prediction. And at NeurIPS 23, what we have done is to actually compare to that. And now we can do exactly the same that we did back then, just 10,000 times faster in a single forward pass. The MCMC was pretty slow, and we had to be pretty smart about running the MCMC on the CPU while the network was training on a GPU in order to use this for hyperparameter optimization. Now it's like almost instantaneous to get the predictions, and the predictive quality is actually even a bit better. So yeah, it was very nice to have come full circle on this. And then finally, we have also looked at this for in-context freesaw Bayesian optimization, where we have a prior over how different hyperparameters actually cause different learning curves. So it's a joint prior over hyperparameters and the learning curves. And long story short, the predictive quality is just much nicer. So here's these much cleaner probabilistic predictions than some other deep learning methods previously, and that also translates to better freesaw Bayesian optimization. So I think there's immense potential in AutoML for using PFNs, and I strongly encourage you to follow up on there. I think, it's a goldmine. All right, what we have focused on since is tabular data. And again, so TabPFN is just a PFN with a prior over tabular data sets. So the typical picture for PFNs drawn for tabular data is as follows again. So we sample data sets, and the data set here is now this is X train, Y train, X test, and this is what we want to predict. We take out the Y test, we feed the rest here into a PFN, parameterized by theta, that outputs some distribution, and then we look how likely is the true Y test under this distribution. That's our negative log likelihood. We minimize it, and off we go. So one sample data set here is actually sort of the equivalent of one data point for a standard SGD training. And so we sample millions of data sets and train over these in order to make very good predictions. And then once we have trained the PFN, we move it over here. It has these parameters, theta star, that are the result of training for millions, in particular in our Nature paper, like 130 million data sets. And then here we truly don't know this, and we make a prediction for it. Right, so TabPFN approximates the Bayesian posterior for the prior that we define over data sets. And then it all comes down to how do we define this prior? And what we did here, in particular, the first author, Noah Holman, is to integrate principles from causality. So we looked at structural causal models. And so it's all about how do we define a prior over data sets. And so he defined a prior over graphs, where we sample and initialize a causal graph with some links and some weights and activation functions. And we also sample where in this graph is the y, where is the x1, where is the x2, etc. And then we sample data from this graph, and we sample it by actually instantiating these root nodes here. These epsilon nodes are noise variables that for each data point we instantiate differently. For example, here 0.7, 0.3 are these epsilon 1, epsilon 2. We do a deterministic forward pass through the structural causal model to get the values at each of the nodes and read out, this is supposed to be the y, that's supposed to be the x2, that's supposed to be the x1. Here we have a data point, and a second data point, and a third data point. For regression, we would leave it like this. For classification, we thresholded, for example, for binary classification, just one threshold. And so now here we have sampled one data set with 3 data points. In practice, we sample hundreds of millions of data sets with up to maybe 10,000 data points, and then learn a classification or regression algorithm on that type of data. We also have in the prior a higher likelihood for simple functions in order to give simple explanations and not overfit to simple data. So we can fit functions like this with lots of latent variables in the graph and so on, but functions like this that are simple are much more likely. And then when we actually sample data sets from this prior, they look to the naked eye sort of similar to real data sets over here, where this is just the two, like one feature plotted against the other feature. And some that have like binaries, some that are ternary, and so on. And basically, intuitively, we then make some of the points here training data points and some test data points, learn to predict from the training points the test data points. And if we can do that for hundreds of millions of data sets, then at some point we just learned an algorithm that can do this. And this algorithm actually predicts very smoothly. So for some of this toy data here, it makes just very smooth and well-calibrated predictions in contrast to traditional algorithms that are based on trees, such as CatBoost. It's just very axis aligned. I sort of really helped to form the AutoML field. This slide here sort of suggests that you don't need any of this complex AutoML anymore. Like this is the pipeline for AutoSQLearn, doing meta learning, doing Bayesian optimization over machine learning pipeline that's really complex, building an ensemble in the end. Here, you actually don't need that. All you need is a network and you do a forward pass. And that is it's pretty powerful. You can just take this network and encode it in Onyx, put it on a sensor, and then you have the sensor where a new machine learning algorithm is running. It's not a predictor, but it's an algorithm that actually can compute a new function based on different inputs. And I think this is a really, powerful for foundation models. But don't despair, AutoML is not dead. It will come back in a couple of slides and make this yet a lot better. So we still have a lot of research to do in AutoML. Quantitatively, this was in 2023. We got better performance in 1 second than any other machine learning or AutoML method in 1 hour, or on average. So here we had AutoScaLearn back then was the best method in an hour, and TabPFN on a GPU was actually something like 36,000 times faster. If you don't have a GPU, only a CPU, it was only like 3,600 times faster. But so really nice, but huge limitations back then, which is also why we haven't seen it be fully adopted or really adopted in a lot of cases at all. Because it was limited to 1,000 data points, 100 features, 10 classes, it only worked for numerical data, no categorical features, no missing values, no uninformative features. So all the stuff you have in data science, and it all needed classification, not regression, and had this very high inference time. And what happened since in TabPFN 2 is we worked a lot on actually resolving these limitations. So now we're good up to 10,000 data points, 500 features, and now we also designed it for categorical features, missing values, uninformative features, all the stuff you have in typical data science problems, imbalanced features, imbalanced data, also regression, not only classification. And we also reduced the inference time. So the inference time used to be particularly high because there's no real difference between training and inference for this. It's a foundation model. You just feed all the data in your context for every test data point that you want to predict. You can predict like 1,000 test data points at once, that's fine. But if you want to, like 10 minutes later, do another prediction, you have to feed the entire training data again. And as such, while the training is fast and while you don't need hyperparameter optimization and so on, and so that's why it was much faster here also than XGBoost, etc. At inference time, it is actually quite slow compared to, for example, an XGBoost that takes your data point, passes it down a tree and predicts. We just need to pass it together with all the training data through a big transformer. Well, not that big, but it's a transformer. And so we're much slower. And what we have done since is some KV caching, so where we cache a lot of the values so that we don't need to do a lot of repeated computation for every new test data points. All right. In a bit more detail, what we've done really is scale up, have a more efficient attention mechanism to support more data points, the change in the architecture to support an arbitrary number of features, and these inference speedups that I just mentioned. And most of the work really has gone into improving the prior. We have trees in the structural causal models. We have more activation functions in there like sines and exponentials and so on. We discretize categoricals in the prior already. So the prior really becomes native about categoricals and then just a lot of engineering. And also importantly, while we call this a foundation model, we demonstrated a lot of foundation model capabilities already in the paper now. All right. I mentioned the new architecture. So while previously we took one row and actually had an embedding for one row at a time, here we now have axial attention on one attention over the features and then one attention over the samples, and that then followed by the standard MLP. And that is iterated 12 times for 12 different layers. And then you take the output from here and feed it through a small MLP to get, again, this bar distribution, this histogram distribution. All right. Qualitatively, because of all the work on the prior, we can now fit a very broad function class. So, for example, things like step functions, where like, you just, of course, can't fit with a linear function. MLPs have their issues with step functions, but TabPFN can quite well approximate this. And of course, like smooth functions like linear functions or quadratics and so on. If you look at what CutBoost does, it makes sense to have these types of just constant predictions. That it gives you good RMSE often, and doesn't give you like very bad outliers. But in many applications, you actually want to know that this is a smooth function and not like a constant function or like something like this. You actually want to predict that this is actually a sinusoidal that's growing. One other nice thing here is that like we didn't have to do anything in order to make it handle heteroscedastic noise. So if you have some data here, nothing in between, then it interpolates well and also says, well, I'm not quite sure about the noise, but interpolates that the noise is growing over the x-axis. All right. Qualitatively, it can also output a multimodal prediction. So this is for nature. We did this double slit experiment because it felt like very physical. So the task here is at each x value, you have this multimodal distribution over these 5 different modes, and it could do this actually very nicely compared to something like CutBoost. All right, then we quantitatively analyze this, of course, to a lot of detail. We looked at the industry standard, the OpenML, AutoML benchmark made by a lot of great people, some of whom surely are in this call. We looked at the subset of 29 datasets from this with up to 10,000 data points and 500 features, then the tenfold cross-validations and reported averages. And in all of this, used a single trained TabPFN. And this TabPFN was actually quite cheap to train. So this trained for 5 days, some trained for 5 days. There are also some that trained for 12 days. I'm not sure if this number is correct, but surely what's correct is that this was on one machine and an old machine, like with 2080s. So 8 2080s. These are gaming cards from 5 years ago. So really, no comparison to the billion-dollar training runs of GPT. And this was for classification. For regression, we also used the corresponding OpenML CTR dataset. For classification, we have this comparison here against linear regression, MLPs, SVMs, random forests, and then 3 different boosting mechanisms, boosting methods that are quite similar. And then TabPFN in dark blue here, the default, and in light blue, the tuned version. Definitely one insight of XGBoost is the default is pretty poor, and when you tune it, it definitely gets better. CutBoost default is much better than XGBoost default. That's why we compared to CutBoost throughout the paper. When you zoom in, it's just even the non-tuned version of TabPFN in like 2.8 seconds here was better than the tuned version of these in 4 hours. And the same you see in this plot here. And this is default against default. There is one data point here where TabPFN default is worse than CutBoost default. So this does still exist. We're making no claims that this is always better, but it is very often better. For regression, the results are not quite as good, but still clearly the best method. But you do see a few more data points here where the second best method is better. We also compared to AutoGluon, which hands down is the best AutoML method for tabular data these days. We sort of stopped maintaining AutoScaLearn, and AutoGluon just incorporated all the great ideas that Matthias had in AutoScaLearn, and has really great engineering on top. So kudos to Nick here. But for small data sets now, actually, so TabPFN is better than AutoGluon for categorical data. Even the default of TabPFN is actually a little bit better than the tuned AutoGluon after 4 hours. And but for regression, actually, the default TabPFN is quite a lot worse than AutoGluon. When you tune it, it becomes about the same. But when you then also put in the post-hoc assembling that really drives a lot of autogluon, then yeah, we get some AutoML back and actually go from the blue to the green here, make it much better. In particular here in regression, that makes us get this win rate of 0.7 compared to autogluon. All right. Yeah, I mentioned uninformative features. There, it does work now. So in order to test this, we added for each feature 9 uninformative features to the actual feature. So if you had like 100 features, we add like, or say we have 10 features, we add up to 100 features. We fill up to 100 features by uninformative features. And TabPFN v1 had big problems with this. MLPs have big problems with this. So there's a big jump down. But for TabPFN now, there's not much of a jump anymore. Actually, even with this, with all these uninformative features, it's still better than CutBoost with only the right features. And how did we do it? Just by changing the prior, telling the prior, well, there might also be a bunch of uninformative features, and that's all we did there. It's robust against missing values. Again, all we did is change the prior, tell it some features might be missing, put a none there, and let the network figure it out. And categorical features, yeah, I mentioned we changed the prior quite a lot. And yeah, I also mentioned previously that it works with less samples. So here with 50% of the samples, it's just about as good or maybe slightly better than CutBoost with 100% of the data. All right, I mentioned the foundation model capabilities we looked at. So as part of the paper, we looked at fine-tuning. So fine-tuning, it's this visualization here on the right. So if we have these orange data points, we're not telling TabPFN that it's a sinusoidal. So you have to kind of think that the function is not there, but only the orange data points. And from that, it's supposed to figure out what the function is. It doesn't do that perfectly. But if you fine-tune it a little bit on a couple of sinusoidals, then it actually, yeah, predicts sinusoidals with much greater probability. So it's like Llama, you can fine-tune it to a particular type of data. As a foundation model, you can also prompt tune it. There was a New York's paper on that with Colin White. You can use it for data generation. You can use it for outlier detection. And yeah, we also have extensions for drift resilient version where we have data drift and we actually find out the data drift just by changing the prior. We have work on counterfactual fairness that falls out really nicely actually in this framework. There's great work by Andreas Müller on using a hypernetwork to output a fast predictor to get around this problem of slow prediction. So here, instead of outputting the y value, it outputs the weights of a small neural network such that when you feed the y-test into that network, x-test into that network, and that network predicts a y-test that is close to your y-test, and you can backprop through this whole hypernetwork. And so that's very cool work. I think Andreas said it's now accepted at iClear. Yeah, also interpretability. With Andreas, we have this work on GAM former, where you output not a hypernetwork, but actually just the shape functions. And so you output a GAM, basically, a generalized additive model, where for a new test data point, all you do is look at the values, like look at a lookup table, basically, of what the score is for that lookup, for that particular value, add these up and get your prediction. And it's just A, super fast, and B, also super interpretable. So I'm really excited about this work. Yeah. And then after publishing the paper, we were very surprised that it actually works really well on time series data. So my master student, Liam, actually looked at this, and looked at time series forecasting, where basically we take this historical data as the X train. The Y is just the height of the time series here. This here is the X test, and we want to predict the height of the X test. And that is just then a tabular problem that goes into TabPFN. And surprisingly, TabPFN then actually gets the first place on this gift eval benchmark, which is that was in Europe's DBT paper last year, which is sort of the typical benchmark used these days now for benchmarking time series. And this is just so surprising to me because this hasn't ever seen a time series. It has never seen a real data set even. And it's still better than just very specialized foundation models for time series such as Chronos by Amazon or TimesFM by Google with large author lists. So I think this goes to show that there is just really so much room to improve these foundation models and a lot to be gained as a community. So I'm really excited for taking TabPFN and fine-tuning it for time series and making it yet a lot better. All right. There's some work left to be done. We do need to scale up. 10,000 data points is not a lot. I would not run this right now for data sets with tens of millions of data points. Their XGBoost is still great. I do expect that we will see a lot of work in scaling this up. We have already seen some work where it's now best on like 100,000 data points, or other foundation models are strong on 100,000 data points. I think by the end of the year, we'll be at 1 million, where this is sort of state of the art. Scaling up the network, looking at scaling laws, coming up with yet better priors, domain-dependent priors, faster inference. I think we can do a lot more. I'm really, I would love to get input from this community about mechanistic understanding. We know why it works. It's approximating Bayesian inference, but we do not know how it works. Which layer does what, at which point in the training is what learned, how important are the different parts of the prior, when does the learning not work, what are the failure modes? I think we just really, there's a lot to be done there. That's really important scientific work. Also, I think that the future of data science is not data. It is data-centric, not model-centric. So right now, data scientists often have to try different models, hyperparameters, but this is really a distraction from actually understanding the data and the objectives. Preaching to the choir here as AutoML folks, I think you agree. We don't want the data scientists to waste their work with that. We want them to actually spend time with the data and tell us, like, these are not the types of patterns we expect. These are the types of patterns we expect. Use the knowledge of the data scientist and just build a better PFN for the data at hand, or fine-tune PFNs, etc. So it's not more coding of different algorithms, but it's just specify the data for which you want to work well and make the PFN work well for that. And that can then also really lead to much quicker iterations with the user and spending the time where we need to spend the time in preference elicitation and understanding the objectives in different applications. All right. Finally, interpretability, explainability, fairness, causal understanding. I do believe that foundation models will be used almost everywhere in the industry. And there are a lot of opportunities because we can actually make them much more interpretable than previous methods. Everyone who says that trees are interpretable, I agree, but XGBoost is not interpretable. It's just like looking at thousands of different trees and so on. It's just not helpful. And also, it's not very smooth. And we already showed in the Nature paper that the SHAP values that you get out of TabPFN are much smoother and much cleaner than the ones out of XGBoost. We can also do like other interpretability studies, like how important is each data point. You can backprop through the network and then say how important is each data point. Like for a traditional MLP or a traditional XGBoost, you would have to backprop through the training process. That would be ludicrous. But for us, it's just backprop, like where we normally forward prop. It's just backprop same time in order to get this usefulness of each data point. I think we can make it more fair by actually taking as inputs, well, these are protected variables, please treat them specially. That's what we're doing in this counterfactual fairness paper. And the causal explanations, well, we already have a Bayesian procedure over structural causal models. Now it's simply a matter of actually accessing which types of causal explanations it uses. I think there's a lot to be gained there. And I think causality is really can be at the forefront of understanding what these models and other models do in the future. All right. So to wrap up, I do think the tabular foundation models are ushering in a new area of data science. There's many opportunities. Time series, I haven't even talked about relational data, causal discovery. We can build a tabular system, and it's really up to us to shape this field. And I hope, yeah, for the good of humanity. So let's work together and make this a reality. Thank you.